You ever look up and see a 400-ton jumbo jet just hanging in the sky, and you think to yourself, how is that even possible? I mean, it just seems to defy all common sense, right? Well, today, we're going to pull back the curtain and unravel that very mystery. It is a fantastic question. How does something that heavy stay up on something you can't even see? The answer, it turns out, is this incredible interplay of physics and engineering. It's like an invisible dance between the plane and the air itself. And to really get this dance, we have to start with the dance floor, the air. The science of how things move through fluids like air is called aerodynamics. But you know, the real secret to flight, it isn't the engine, it's not even the wing, not really. It's in a property of the air you might not expect. Yeah, here's the absolute key. Air is not empty space. It's a substance, it's a fluid, and it has physical properties that we can actually use. And for our story, the most important property is something called viscosity, which is really just a fancy word for its stickiness. So yeah, let's take a much closer look at this fluid we call air. When we really zoom in on its properties, we find the first big clue that unlocks how flight is even possible. And that property is called viscosity. The easiest way to think about it is like a super, super thin version of honey. Air has this internal friction, right? It causes its own layers to kind of resist sliding past one another. It wants to stick together. And, this is the crucial part for flying, it wants to stick to surfaces moving through it. This diagram here shows it perfectly. See how that top plate moves? It's literally dragging the layer of fluid right next to it along for the ride. That's viscosity in action. And then that layer drags the one below it, and so on down the line. This is exactly what's happening on an airplane's wing. A super thin layer of air, we call it the boundary layer, sticks right to the wing's surface and gets pulled along with it. Okay, so the air is sticky, but that doesn't mean it always behaves the same way. Not at all. Depending on the situation, this flow of air can look like one of two completely different things, either a perfectly disciplined army or a totally chaotic mob. On one hand, you've got laminar flow. It's smooth, it's orderly, it's predictable. And on the other hand, you have turbulent flow, which is chaotic, swirling, and just full of messy energy. For an airplane, knowing which type of flow you have and where you have it, that's everything. And you can see the difference right here. Look at the left. That's your laminar flow. It's like a marching band in perfect, beautiful formation. Now look at the right. That's turbulent flow. It's basically a chaotic mosh pit. One is efficient and orderly, the other is disruptive and messy. And controlling which one you get is the key to flying. So, how in the world do engineers predict if they're going to get the marching band or the mosh pit? Well, they don't guess. They use these incredibly powerful tools, a kind of secret language written in what are called dimensionless numbers. Let's start with the big one, the Reynolds number. The best way to think about it is like a tug of war happening inside the air. On one side, you have inertial forces. That's the air's tendency to just keep moving in a straight line. And on the other side, you have the viscous forces. That's the sticky internal friction trying to keep everything nice and orderly. The Reynolds number just tells us who's winning that tug of war. So at a really low Reynolds number, viscosity, the stickiness, is the clear winner. You can see the flow is smooth, it's orderly, and it just wraps perfectly around the object. This is that beautiful, pure, laminar-like flow. But watch what happens as we crank up the speed or the size of the object, which increases the Reynolds number. Now, inertia starts to fight back. You can see right here how the air can't quite make that sharp turn around the back of the cylinder anymore. It starts to peel away, creating this little separation bubble. The tug of war is definitely getting interesting now. And boom, at an even higher Reynolds number, inertia is totally dominant. The flow can't stay attached at all. It just breaks away into this chaotic, swirling, turbulent wake. That orderly marching band has turned into a full-on mosh pit. And understanding this transition is absolutely fundamental flight. But the Reynolds number isn't the only number in our secret language. When things get really, really fast, we need to talk about the Mach number. All this tells us is how fast we're going compared to the speed of sound. And this is critical because as you get close to the speed of sound, the air starts to get squishy, it starts to compress, and all the rules of our little dance change completely. Take a look here. At about 73% of the speed of sound, Mach 0.732, the flow over this wing looks pretty normal. It's fast for sure, but the air is behaving predictably. It's flowing nice and smooth over all the curves. But just watch what happens as we get closer to Mach 1. You see those dark, sharp lines? Those are shock waves. They're forming because some of the air, as it speeds up over the wing's curve, actually breaks the sound barrier before the plane itself does. And these shock waves, they create a massive, sudden change in pressure. They are a huge challenge in designing high-speed aircraft. Okay, so we've got our building blocks now. We have that sticky viscosity, we have laminar and turbulent flow, and we have our secret numbers. Now let's put it all together and see exactly how a wing pulls off its magic trick. This shape here, this is an airfoil. It's the cross-section of a wing. You can think of it as a precision instrument that's designed for one thing, to manipulate the flow of air. That curved top forces the air to speed up, which creates lower pressure. At the same time, the angle of the wing is pushing air downwards. That combination of low pressure on top and pushing air down, that generates the upward force we call lift. But it only works if the air decides to cooperate. And this right here, this brings it all home. On the left, the wing is at a nice, low angle to the air. The flow is smooth, it's attached, it's our orderly marching band. This wing is making lift. But now look at the right. The pilot has pulled the nose up too high, the angle is too steep. And just like our cylinder at a high Reynolds number, the airflow can't make that sharp turn. It separates, it detaches from the wing, and creates a massive turbulent wake. Lift is destroyed. This is a stall. It's why pilots train endlessly to avoid it, and it's why that angle during takeoff and landing is so incredibly critical. So you see, flight isn't really about floating, it's about control. It's a delicate dance where the airfoil shape leads and the air follows. As long as that flow stays smooth and attached, you get lift. But the moment that connection is broken and the flow separates into that chaotic turbulence, the dance is over. The lift is gone. So we've basically cracked the code for how to fly here on Earth. But think about this for a second. Mars has an atmosphere that's about 100 times thinner than ours. Saturn's moon Titan has one that's thicker and way colder. The principles we talked about today are the starting point, for sure. But what new shapes, what new rules will we need to figure out for those invisible dances on other worlds?